Assalamu alaikum everyone. My name is Alaa. I'm a fifth year medical student, and today I'm very excited to be giving you the acid and base lecture. I understand why this lecture might be very intimidating to a lot of you. A lot of the terms and equations and whatnot seem a lot more complex than what it should. But inshallah, through this lecture, we're going to go through it together. We're going to oversimplify everything, and I'm going to be giving you only the high yield information for your exams. I've included my phone number and email. Please make sure to reach out to me if you have any questions or if you require any further explanations. Now, I always like to start off with a short dua before studying. So make sure to pause at your own time and go read it. Yalla, for learning objectives, it's important to note that this is going to be part of the first part of a two-part session. I'm going to be giving the first part and someone else will be giving the second part, inshallah. Now, let's start with defining some basic terms. So we all know that our body likes to be in homeostasis. Everything inside our body should be properly controlled. Equilibrium should be maintained so that the body can function normally. Any deviation from this normal equilibrium would result in diseases. So an example would be diabetes, for example. If you have high glucose in your body, results in pathology. If you have low glucose in your body, again, results in pathology. So pH is very similar in that matter, and it needs to be regulated very well. If pH is too low, it's bad. If it's too high, it's bad. Now, this buffer system, our key players are the lungs and the kidneys. They play a major role in maintaining the pH of the body. That being said, if lungs or the kidneys are affected, this would result in disease. This would result in diseases, and the pH would not be properly maintained within the body. So everything should be at a perfect balance in our bodies. And this is why pH should be maintained within the blood between 3.75 and 7.45. Again, if deviations occur within this normal range, patients would experience disastrous manifestations. So it's very important that pH be kept between 7.35 and 7.45. Within the cells, pH is a bit more acidic, so it can be from 6.8. pH will start from 6.8, and within the cells, within the blood, it's 7.35 and a maximum of 7.45. So this is the only acceptable range. Beyond this, it can be acidotic, so your pH would be more on the acidic side and would result in acidosis. Above that, pH would be higher and would result in alkalosis. So it's very important that it is maintained strictly within this range, okay? Now, I've been talking about acids and basic, but let's go back to let's go a few steps back and define some basic terms. So what is an acid? An acid is a substance that releases hydrogen ions. So we have this molecule right here. This molecule has hydrogen and it has A. A represents some random molecule that we don't care about in this example. But what's important is the H molecule. Now, HA will dissociate or will divide to give us hydrogen ions and the negative ion of A. So, by definition, HA releases hydrogen ions and this makes it an acid. So by definition, anything that releases an acid, anything that releases a hydrogen ion is in fact an acid. Okay? Now, bases. A base is a substance that accepts hydrogen ions, so it's the exact opposite. We have here in the negative version of A and hydrogen ions, we see that it forms HA. Through this equation, we see that hydrogen combined with A minus accepted hydrogen ions to form HA. So by definition, A is a base because it accepted hydrogen ions. Okay? Now, the doctor gave you guys a few examples here, so we'll make sure we'll go over the first one so that everything is a bit more clear. You have ammonium. Ammonium can form NH3 and it can form hydrogen. So ammonium releases hydrogen ion and NH3. So what does that make it? It makes it an acid because it releases protons. Now, for NH3, you can see that it accepts hydrogen ions to form NH4. So what does that make it? It makes it a base, okay? So we've discussed the terms acid and base, and we've discussed how based on whether a molecule takes up hydrogen ion or releases it, it can be defined as a base or an acid. However, there's something else that I want to bring your attention to. So these reactions are very special. Why? Because you'll notice this symbol. Let me just circle. So this symbol makes these reactions very special and very different than all other reactions. So what does this symbol tell us about these reactions? Number one, it tells us that these reactions can be in equilibrium, meaning these reactions can come to a state where the reactants and the products stay at the same concentration, right? It also tells us that this reaction can not only go in this direction, as it can go in the backwards direction as well. So not only would it go this way, it can go this way as well. And this continuous back and forth can result in basically a reaction that does not end. So reactants will combine together to form a product. Products will either break down or combine together to form a reactant. So it does not end, and it's sort of like a cycle of reactions. This feature of these reactions makes them very special. Why? Let's see. So these reactions love to stay in equilibrium. It hates anything that disrupts their equilibrium, and it does not allow it. So one day, if I decide to interfere with this equation and add extra hydrogen ions, this reaction would hate that so much, it would try to nullify the effects that I induced. So what would happen? It would try to get rid of the extra hydrogen ions that I added by forcing the reaction to go to this direction, forcing the reaction to utilize hydrogen ions so that HA is formed. Okay? Tamam. So this reaction has the potential to cancel out any change that I add to it, and it has the potential, it has the power to stay in equilibrium. So no matter what I do, up to a certain extent, of course, but no matter what I do, this reaction will not allow me to change its equilibrium. Now, why is this very special? Why is this feature very special? Is because I can explain this using an example. So we'll have our human here. So this human, of course, they have blood in their vessels. So this blood has buffer systems, and I'll talk about what buffer systems are in a bit, because their blood has buffers in it. and it has reactions that are in equilibrium. So what happens is, if one day I decide to come in and inject hydrogen ions on this patient, um, so one day I come in, I feel evil. I go to a patient and I inject hydrogen ions in their system. So what happens then? The body will not allow these hydrogen ions to make a change to this patient. And how does it do that? It does it by equilibrium reactions that are in equilibrium. So what will happen is, I injected hydrogen ions. The body does not like it. The reactions that are in equilibrium will not let me. And what would happen is, this hydrogen will be utilized to form this HA. So, as an outcome of this, the hydrogen that I injected barely has any effect on this patient. So through this equilibrium reaction, the effect of hydrogen ion injection was buffered, right? So by definition, a buffer is something that reduces the impact of disastrous impact of something. Okay, so if it weren't for these buffers, this patient would have suffered from disastrous manifestations. But because of these because of the buffers that are present in the body, the body is not as affected by the hydrogen that I injected. Okay, so this is sort of how these buffers help us overcome any changes to homeostasis. Okay, it ties back to our homeostasis slide. Everything should be in perfect balance. Okay, so we talked about acid, we talked about base, and we talked about what a buffer does. Now, let's go on to more important or more big girl and big boy type of information. So we have hydrogen, we have this equation that I just talked about. Now, these ions, we said this reaction, we said that it always stays in equilibrium. No matter what we try to do up to a certain extent, it'll nullify whatever effects that we induce. Okay? Now, generally, let me actually start screen sharing from here. Okay. Okay. Just delete. Okay. So, what happens is you have this reaction, the right side of the equation, and you have the left side of the equation. As I said, these two sides need to always be in equilibrium. They will not allow you to induce any change in them. The concentrations of either side will always, or will try to always stay in equilibrium. So what happens here? You have, let's say, you have a concentration of 2 HA, and this side is just 1. Okay, or let me just remove. Okay, right. So you have 2 HA. This is the let's pretend it's the normal concentration of this reaction. The concentration of HA should be 2 in order for us to have 1 A minus and 1 H plus. So let's say this is the normal. Because these reactions are in equilibrium, they will never allow me to change this ratio between the right side of the equation and the left side. So if one day I try to change it and induce a change, I change this 2 to a 4. Okay? So what would happen? The reaction will not like that. It will try to maintain the ratio between both sides of the equation, and it will double this side. Okay, so all of this in an attempt to have the ratio between the right and the left stay the same. Now this ratio has a name. We call it the equilibrium constant, or K. Okay, it's denoted as the letter K. Now, this K is essentially a measure of the ratio between the right side of the equation and the left side of the equation. Tamam? So, we talked about the equilibrium constant. Now, this equilibrium constant, or this equation rather, this whole thing, is referred to as the law of mass action. Okay, so this part is referred to as the law of mass. From the law of mass, we can do some things and change some things and move things to the right and left and come up with another equation called the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation is essentially the logarithmic form of this equation. Okay, so when you get the logarithmic form of this equation, you end up with the Henderson-Hasselbalch equation. Now, you don't need to know how you get the Henderson-Hasselbalch equation. You don't need to know what the logarithmic form is. You don't need to know any of that. All you need to know is this. You have your Henderson-Hasselbalch equation. Now, this is very important because I remember we used to be asked about this and asked about any parts of this equation. So you can be asked how to calculate pH or how to calculate this ion and so on. So it's important that you know this. But yeah, essentially, this is the Henderson-Hasselbalch equation. Let's try to familiarize ourselves more with it. So we know what pH is. We know what A minus is the base essentially. And we know what HA is. HA is the acid. So base over acid. And then the log form, okay? Now, what is pKa? We know what the rest are in this equation, but we don't know what pKa really is. So pKa, essentially, it's a negative log of the inverse of K. You don't need to know this. I'm just telling you so that everything sort of ties together, okay? So okay, now that we know how pKa is derived, but what is pKa actually? pKa measures the acidity of an acid. So it measures how acidic a molecule can be. And that's it. This is it for this part. It's pretty simple, inshallah. Move on to the next part, next slide. Now, not only did they make a complicated equation, but they decided to make a complicated curve out of this complicated equation. This, inshallah, we'll explain it, and it's not going to be difficult at all. Now, whenever you look at a curve, the first thing that you're going to want to look at are the axes. Okay, so you look at the y-axis, you look at the x-axis, and see what does each one of them denote. Y-axis talks about plots the percentage of the base. Y-axis plots the pK in relation to the pH. What does that mean? It means, let's take it as an example. Maybe that'll make it easier to understand. So if pH is 2, if let's say pH is 2, so that means at this point where pK equals pH, pK will be 2. And at this point where pH equals pK plus 1, pK will be 1. And at this point where pH equals pK plus 2, this will be 0. Okay? I hope that makes it more clear. And you'll notice a general trend. Or actually, okay. So this is it for now. Then we'll look at. Then he was telling you to look at the slopes of the curve. So he was looking at this slope. He looked at this curve from different points, right? He looked at it at this point, looked at it when PK was PK minus 1, he looked at it at PK, and he looked at it at PK plus 1. Okay, they were trying to see what the trend exactly is. Now, before I start talking about this curve, I want to put in a few basic rules. So generally, with any curve, the steeper the curve is, with any graph, the steeper the curve is, the quicker the reaction, the faster the reaction, the more efficacious whatever you're testing is. Essentially, يعني, the steeper the curve, the better, okay? Or the quicker, okay? But if a graph is less steep, you know that this is a lazy reaction. It's very slow. It does not yield any fast results, whatever it is, depending on what the labeling of the axis is. But this is a general term. So now, when we look at this graph, we'll try to identify the graph at the slope at several points in this graph. So we have this point, okay? We have this point, and we have this point. Type. So if this was a curve, if we plot these slopes together, let's actually take these slopes and put them here. So this is one, this is another, and this is another. So what does this show us? It shows us that this slope, number one, at this point, is actually the steepest. So what does that indicate? It indicates that the buffering is best at this region, is better at this region. Now you look at the second one, which corresponds to this area. What do I put to here? Type. So it'll indicate that at this area, the slope is a bit more flat compared to this area, and so on. The third is the flattest one out of the three. Okay, so when you look at these different trends, it shows us that the highest point of efficacy or the steepest slope is this one. And when you go to this slope, you'll see that it corresponds to pH equals pK, okay? So this is the first point. And when you look at the slowest slope, let's compare the fastest and the slowest. When you look at the slowest slope, it shows you that it corresponds to pK plus 1. So that leads me to believe that the more the difference between pK and pH, the less the efficacy or the capacity of this buffer. Okay, let me repeat that in simpler terms. So in this area, the buffer was the best. It did a phenomenal job. Why? Because the difference between pK and pH was 0. In this point, the buffer was a bit slower. And when you look at the pK and the pH, you'll see that the difference is 1. Okay. Now all of this talk is just to say one point. It's just to explain one main point, and that point is to determine the capacity, or in other words, to determine how good a buffer is. So how do you determine capacity of buffer? Or in other words, how do you determine how good a buffer is? It'll depend on two things. One of the things is the one that we just mentioned, the difference between pH and pK. The more the difference, the less the capacity, meaning the more the difference, the more weak the buffer is. Second, it's not really related to this graph, but they're essentially saying that the less the concentration of buffer that you have, the weaker or the less the capacity. which makes sense. Yani if I have less of, if I have a very few reagents, of course, yani the buffer is not going to last long, and you would have less efficacy, right? So the lower the concentration of a reagent, the less the capacity. طيب, so this graph proves these two. Now, not only did they look at that, but they looked at the exact points where a buffer is considered of lesser capacity. And they found that in this area here, this is the area that we were talking about, around 1.22, they noticed that beyond this area, beyond this graph, the buffering capacity will be very weak. So they determined that whenever the difference between pK and pH is more than 1.22, that means this buffer will have very low capacity. That means it's not a good buffer, okay? Of course, the same is true for the extremes. So same thing would be here. Not only that, but because we also discussed that the less the concentration, the less the capacity. In this area, you have lesser concentration of base A. So this area would not be ideal. In this area, the buffer capacity would not be good. So in this area and this area, the buffering capacity would not be good, okay? Buffers that are good are from here. Okay, hope that's clear, inshallah. And he repeats it here again. The buffering capacity depends on pH minus pK and the concentration of the buffer. Tamam. So that was the first point. Now he looks at specific examples of buffers within the body, okay? Or specific examples of reactions that are in equilibrium within the body. So let's look at this graph. It has the pH at the bottom here, and it has the concentration of the base here. And they mentioned the pKs here. Now, applying this rule that we talked about, we're going to, for this example, we're going to only be applying the first rule. So pH minus pK. We're going to ignore the other rule for now, because we're going to be looking at it in more detail later. So let's take it one by one. The first one is the lactate buffer. So this lactate buffer, it has a pK of 3.9. Okay, we'll see. pK is 3.9. And what is the normal body pH? Normal body pH is 6.8 intracellularly, extracellularly 7.35 as a minimum, yani. So what are we going to do? We're going to subtract these from each other, and one sec. And the results, okay? So we're going to subtract the pK and the pH from each other. 6.8 minus 3.9. This will give us, I think, 2.6 or something around that. Basically, yani what all we care about, is it more than 1.22? Yes, it's more than 1.22. Khalas, end of discussion, it's not a good buffer, okay? So this is not able to buffer, is not able to act as a buffer within our bodies. Now let's look at another buffer in our, let's look at another reaction that's in equilibrium in our body. This is this reaction, okay? So we'll look at the phosphate reaction. So we'll look at the pK, okay? So let's take a look at the pK. pK is 6.8, okay? Maybe that, and then we look at the body pH. So intracellularly, pH is 6.8. Extracellular, pH is 7.35. So when you subtract, it's actually an excellent buffer intracellularly, because there is no difference at all between the pK and the pH, right? So yani it's a very good buffer. What about extracellularly? Again, the difference, as long as it's less than 1.22, I do not care. It's a good buffer. I'm not any خاص. Less than 1.22, it's good. And it is less than 1.22, so that means that it satisfies the first part of uh, the capacity of the buffer. So we said this one has bad capacity, this one has good capacity. And when you look at this one, again, it's the same idea. You subtract the pK, 9.4, from the pH, which is 6.8. Again, if it's too low, you don't consider it and it's not going to be a good buffer. So from all of this, we determine that this is a bad buffer, this is a good buffer, and this is a bad buffer. Okay? Hope that makes sense. Now, in the previous slide, we were looking only at the first condition, which is pH minus pK to be less than 1.22. However, in this slide, we're going to be considering everything. And we're going to be looking at actual examples of biological buffers in the human body. So let's look at the phosphate buffer, first of all. We already looked at it here. We said that it's an excellent buffer for intracellularly, and it's also a good buffer for extracellularly because the difference between pK and pH is less than 1.2. So it's good. It satisfies the first term. What about the second term? Phosphate is actually has a high concentration intracellularly. So for intracellular buffering, it's very good, right? It satisfies both terms. Number one, it needs to have pH minus pK needs to be less than 1.22, and it needs to have sufficient concentration, right? So it satisfies this one and this one. However, extracellularly, phosphate is not present that much. It has actually a very low concentration. So the phosphate buffer does not satisfy the second point for a good a buffer with good capacity. So from this, we can say that phosphate buffer is a good buffer intracellularly. However, extracellularly, it is not. Okay, this is the first example. Second, we'll look at the bicarbonate. So for bicarbonate, the pK is 6.1. Now, for when you calculate it intracellularly, it would be good enough. So it's less than because so intracellularly 6.8 and extracellularly 7.35. Now, intracellularly, it is good. Yes. Do we have carbon dioxide intracellularly? Maybe we do, but it's very little. So it's probably not a good buffer intracellularly. What about extracellular? What about extracellular? So the pK 6.1 minus 7.35, it's going to come out to be more than 1.22. But there's a catch. It being more than 1.22 does not necessarily mean that it's a bad buffer. Why? Because this buffering system has something very special to it, and it's that it's an open buffering system. What does this term mean? It means that when you look at this buffer, for example, everything is contained within a compartment, right? So nothing from the outside really affects whatever is happening. Everything is happening within the cells, okay? However, what do we mean by an open buffering compartment? It means that this compartment is open to the outside, which is very true because carbon dioxide can be exhaled in and out of the body, right? Mostly out though. So you end up releasing a lot of this carbon dioxide outside. And what does this do? it drives the reaction to one side, and it prevents it from being a closed reaction. It's open, it's dynamic, and it proves to be a sufficient buffering system for extracellular. Okay, so this is why it actually is a good buffering system for يعني extracellularly. It is a good buffering system because carbon dioxide can escape to the outside. It's an open buffering system. Okay, hope that makes sense. Now we look at proteins. So proteins, they have and again, this is sort of the same thing, but then proteins are different than all the other molecules. So yani, I want you guys to just like ignore this part in the middle. It's not I think yani, I look at it and it's just a bit of a distraction. So let's just ignore it for now. Whatever, okay, I hate okay, so we'll just ignore the part in the middle. We'll focus on this part and this part. Now, amino acids are said to be buffers on their own. When you look at these reactions, they have several different substrates, several different molecules, but then amino acids are different because they have them on their own, they can act as a buffering system. Okay, so how does this happen? They can act on their own as a buffering system because they have acid and they have a basic area. So let's look into it. This area is able to accept a hydrogen ion and become NH3, right? So this area is accepting hydrogen ions. What does that make it? Basic. What about this area? This area is able to give out hydrogen ions. It can either be COO negative or COOH. When it gives out this hydrogen ions, what does it basically become? Acidic. So it has an acid, it has a base. What does that make it? It makes it automatically a buffer, okay? Now, amino acids, they're all buffers. However, only certain amino acids can act as buffers within the body. Why? Because we already said this before, they need to satisfy these two terms, okay? Most importantly, pH and pK. So let's look at the pKs of these amino acids. So here they have like this graph where they plotted pK of each amino acid on the pH, on a pH scale. Here they're telling you these are too acidic, these are too basic, and the difference is probably more than 1.22. So they're probably not able to act as proper buffers within the body. These, however, are just right. These are more likely, most likely, to have a pH minus pK value of less than 1.22. And so not only are they buffers, but they're buffers that are able to buffer inside the human body. I know that it sounds a bit difficult, but what they're saying is they have buffering capacity inside of the human body, okay? And they can act as actual buffers. Oh, this is all you need to know about this. It's actually very simple. Oh no. Okay. Sorry about that. Let me just fix it quickly. Okay. Let me reshare. Okay. Type. Yalla, let's continue. So pretty simple stuff. Easy, logical. In this slide, he just gives you an example of the carbonate carbon dioxide buffer. he puts in the values so that everything can come into place, and you can see the bigger picture of the whole thing. So what he did, he gave you the concentration of carbon dioxide. He gave you the concentration of bicarbonate. He also gave you the pK of this reaction. It was actually here, 6.1. So, and then they used it to calculate the pH, which turned out to be 7.4. Now, what they did, again, they love graphs. They put it in, and he formed another graph using this data. So what did they do? They took a concentration of carbon dioxide. So initially, they took PCO2 equals 40. But what did they do? They took they used this equation and they calculated the pH for multiple bicarbonate concentrations. So they took bicarbonate of 15 and then 20, and then they calculated the pH each time for it. So let's go to our example. So we had this one. This is what we started with. We had this patient. They took their CO2. They took their bicarb. It turned out to be this. CO2 was this. And then they calculated, and the pH turned out to be 7.4. Okay. And then again, they tried with a different bicarb concentration. They tried with a lower one, and the pH turned out to be 7.2. And then they did this several times until they were able to draw this curve. Not only did they do that, and then they took different concentrations of carbon dioxide as well to show you that when you increase carbon dioxide, the pH, the pH, they're just trying to show you the relation basically. Not very important, not very high yield at all. You just need to be able to know how to read this graph. This again, not very high yield. طيب. So now we'll get to the proper clinical explanations. Because we're talking about the human body, let's start involving the organs and start involving the actual buffer systems so that we understand what exactly happens in the human body. Tamam? So in this slide, okay. So here they're looking at these buffer systems in context of the organs that are present and in context of clinical occurrences. So for example, let's take this example. You have a patient here. This is their lungs. So for this patient, what happens is, let's say that they're stopped breathing and they're unable to breathe. So there's obstruction. Okay, so there's obstruction. Let's say obstruction of the lung. This patient cannot exhale CO2. So what happens is CO2 accumulates, and again, the body hates disturbances in its equilibrium. Anything that disturbs its equilibrium, it tries to get rid of it. So what happens? You increase CO2 a lot, and this will induce this buffer system, the one that we've been talking about, this one. So you increase CO2. This CO2 will combine with the H2O and end up in the formation of hydrogen ions and bicarb. Let's go back and look at it again. Okay, so because CO2 is increased, the reaction will favor this direction. You'll get the production of bicarb and H+ ions. Now, in the body, naturally, you have so much bicarb, a lot more than hydrogen ions. So what does that mean? I talked initially in the beginning of this lecture on the importance of balance between the right side of the equation and the left side of the equation. I told you guys that the equation always loves to be at a balance. It does not like its balance to be disturbed, right? And I told you guys if this is 2 and then one day I add 2 additional and this becomes 4, this becomes 2. صح? Now let's look at it here in the context of this one. So here, what are we doing? Essentially, because you have CO2 and it's combining with H2O, essentially what is happening, you're increasing hydrogen ions, right? The reaction will not like that. It will not be in equilibrium unless you increase everything else. Now, CO2, we're not really worried about. CO2, also, it's already very high from here in the lungs. So what happens is you have high CO2, you have high hydrogen ions, but the bicarb is not high, right? Why? Because naturally the bicarb is not high in our bodies. The bicarb is actually a lot more higher than hydrogen ions. So in order for this reaction to continue to be in equilibrium, if this triples, this needs to triple, okay? And it's very hard to triple bicarb because as I said, it's already a lot, so you can't triple it even more. It's a lot more difficult. So what ends up happening is that the reaction stops being at equilibrium. خلاص, it got defeated. You added so many hydrogen ions and so many CO2, but you failed to increase bicarb. What happens is it ceases to be in equilibrium. This is not good because this equation is not in equilibrium, this CO2, we won't be able to get rid of it. And where is it going to go? Right? Because this reaction, خلاص, it's not in equilibrium anymore. It stopped. It went to this direction and that's it. Okay? We need a reaction that constantly renews itself so that it can constantly keep getting rid of the CO2 that is present. Okay? It's not a good thing that it stopped being in equilibrium. So this is in a situation where only this bicarb CO2 buffer is present. But luckily, subhanallah, we're in our bodies, the situation is a lot more different, and I'll talk about it in a bit. So let's look at this graph first. Basically, this graph, what they're showing you through it is that you have your plasma, you have your partial pressure of CO2, and it keeps increasing, right? It increases. It's higher, but then here it's lower. But yeah. Okay, let's do this. So you have your partial pressure of CO2, and of course, as CO2 increases, the trend in the pH would be to increase. Because CO2 is acidic, right? And it favors the formation of H+ ions. So the trend would be the more you increase the partial pressure of CO2, like in our case here, where you have high CO2, the more you increase the CO2, the more acidic the pH is, okay? So this is how we're gonna read this graph, this side to this side. Okay, so you're increasing CO2. However, when you look at the plasma bicarb, it's not increasing, it's staying at a constant line. This is not good, again, because the equation will cease to be in equilibrium. So what happens, this is when you take the CO2 bicarb buffer and put it on its own. But luckily, it's not like that. Our bodies are actually very different from what we see in a lab setting. So this would be seen in a lab setting. This is what actually happens in our body. So in our body, we not only have this reaction, it doesn't stop here, but we also have a second buffering system. What this second buffering system does is that it takes, okay, let's start from the beginning. You have obstruction in your breathing. The patient has high CO2. this high CO2 will combine with the H2O to form bicarbonate and H plus. Initially, we said in the previous in the previous slide, we said the reaction will stop here because H plus will be high, bicarb will not increase, so the reaction class will be done. But what happens is our body has another buffer system. What this buffer system does is that it takes this hydrogen and it combines it with B. B is another random ion. So what it does is that it takes this hydrogen ion and it combines it with the B, okay? This means that, remember here when we said hydrogen ion will be elevated, elevated, elevated. So in this case, it would not, in this situation, it would not be the case. Why? Because hydrogen ions would not continue to elevate. They will be formed, they will bind with B, they will form HB, and their concentration would not be too high. So what would happen is you won't have increase, increase, increase. In this case, you'll have increase in CO2, maybe okay, an increase in hydrogen ions, but not too much of an increase where it disrupts the equilibrium. And this is good because it allows the reaction to continue, and it allows this reaction to continue being in equilibrium. Okay, so bicarb would be produced, of course. You have high CO2 would combine with H2O, increase the formation of bicarb, increase the formation of hydrogen ions initially. This hydrogen ions will then bind with the B minus, okay? Will bind with B minus so that they would be less, and B minus, of course, would decrease, and you would have high formation of HB, whatever it is. And these are all examples. It's just like an example, yani. Okay. And then when you look at the graph, so this is the graph that we saw before, where bicarb was it wasn't increasing, but then in this example, you'll notice that this is the initial, so bicarb was not increasing. I think it's important to note that the other buffers, so here, other buffers in this area would include things like hemoglobin, would include things like proteins and whatnot. So this B can represent hemoglobin, can represent other proteins, okay? Now, in this graph, he shows you the relation between B and this equation, okay? So notice that when B is 0, you'll have low bicarbonate levels, okay? Here. But then and then he gives several other factors. So this is the example that we looked at before, when hemoglobin was actually 0, when there was no B, okay? Now that you have B, B can be proteins, hemoglobin, whatnot. Let's just take it as hemoglobin for now. So here, he's telling you there is no hemoglobin in this patient. You'll notice that the plasma bicarb is gonna be around, let's say, 24, okay? In a normal patient, the plasma bicarb will be higher, okay? You'll notice that it's here, around 33, okay? So it would be higher, leading us to believe that this reaction, so how does bicarb become higher? The way that I try to remember it and make sense of it is that this reaction will continue, it will continue, it will continue, it will continue, it will not be stopped, right? Because in this one, the reaction would be stopped. because there would be no B, right? We'll just have production of H plus and that's it. And then we said because H plus would be too high, bicarbonate would not increase as much. You need to double it as well. Okay, if you triple this, you need to triple this. But you can't because it's already high. But then in this patient, okay, oops. What's the difference is that you have B, okay? So the equilibrium will not be stopped. The reaction would continue occurring. So reaction would occur, would continue occurring until you have a lot of production of bicarb, and this will help in the increase in its concentration. I hope that's clear. So it would cause an increase in its concentration in the blood, okay? And then he gives you other situations where you have where they just to be sure, they conducted it in patients with excess hemoglobin, and they conducted it in patients with less hemoglobin. So okay, so patients with excess hemoglobin, what do we expect? We expect that the B would be more, so the reaction would be going even more, right? So not only this, okay, so B is increased, so reaction will continue even more to occur. So what will happen? You'll notice that the bicarb concentration would be even more. Okay, this is with polycythemia. With anemia, meaning the patient has less hemoglobin, you'll notice that it is more than no hemoglobin, but it's less than normal amount of hemoglobin, if that makes sense. Yani, the general trend is the more you have of the second buffer, the more this reaction is likely to proceed, the less likely this reaction will stop being at equilibrium. The more CO2 will be released and executed, okay? This is what they're saying through these graphs. And I love this slide so much because it perfectly summarizes what you need to know from this lecture. So there, from the whole hour or however long I've been talking, it can be summarized in 4 main points. Number one, the criteria for buffering capacity. We said there are two important things. Number one, pH minus pK, the difference between them. The greater the difference, the less the buffering capacity. The less the difference between pH and pK, the better the buffering capacity. Second criteria, or second criteria for buffering capacity is that the total concentration of the buffer needs to be high. You can't have a buffer that is little. What good would that make? So that's the second criteria. Then we talked about the buffering properties of the CO2 and the bicarb buffer system. We said because we said even though there's a large difference between pH and pK, the buffer system is actually good because it's an open system, because carbon dioxide can actually be released from the body, and this helps in making it a good buffer system. Second thing that we mentioned is that it's this point here. He says increase in CO2 in a solution containing only bicarb buffer causes no measurable increase in bicarbonate. Okay, now we know that this is true. Basically, he's saying this point. If you this situation where there is no other buffer would result in no change in bicarb concentration. But if you have another buffer, it would cause an increase in the buffer concentration. Okay, this is basically what we described here. Something else that is important to note is that is this point. The bicarb buffer system cannot participate to buffering during respiratory or acid-based disturbances. Basically, what he's saying is that if for example, the patient has patient, and if the original problem is that the patient has a lot of CO2, of course this buffer is not going to work this way, and the reaction is not going to proceed this way. Or if the patient has a defect in the respiratory, he has respiratory acidosis, meaning the patient is unable to exhale carbon dioxide out. This system might not any function properly, because also it is the cause of the disease. So this is what he's saying. It's very simple stuff. So yeah, I think, and this brings us to the end of our lecture. I hope I was able to simplify it a lot more. And please, 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 always feel free to reach out to me if you have any questions. Um, I always encourage people to let me know if they have any questions or anything that they want to be explained. I'd always be more than happy to explain anything. So yeah, inshallah, you guys do really well in your exams. My prayers are with you, and I hope this session was beneficial. And yeah, again, my number was on the first slide. So feel free to let me know if you guys have any questions. And thank you so much for listening to this point. Allah, have a good day.